Hello, welcome to my research profile presentation. I am Saikat Chatterjee from KTH, Royal Institute of Technology, Stockholm, Sweden, and the title of this presentation is Sparsity in Signal Processing and Machine Learning. About myself, I did my PhD from Indian Institute of Science, Bangalore in 2009, and then did my postdoc in KTH, and then currently docent in signal processing at KTH. My broad research objectives are developing technologies for efficient sensing, transmission, and processing of complex signals and large data sets, followed by learning. What does it mean? That means I am interested in efficient signal acquisition, for transmission, efficient source coding parts, and processing of complex signals and large data sets means finding parameters and parameters of different models of complex signals, and then followed by learning means different kind of inference tasks followed by decision. Topics of my research interests are sparse processing such as compressed sensing, statistical signal processing, estimation and detection, machine learning, Bayesian and deep learning, speech and audio signal processing, bioinformatics, big data analysis in biology, and typical big data analysis tasks. In this slide, I show some of the topics in red fonts, and those are the topics we will consider in this presentation. Let us say we start with an example problem in estimation. I have this signal which let us say that we deal with, and this signal comprises of two sinusoidal signals, this signal and these signals. Each sinusoidal signal has typically three parameters: amplitude, phase, and frequency. In this case, I kept the phase angles 0, so that means that each sinusoidal signals are characterized by two parameters. Now, for these two sinusoids, there are four parameters, and from this signal, the task is to find out these four parameters. And typically, you do not see this clean signal in environment, so we always have some kind of environmental noise, and this noise is added with this signal, and we see these observations. So, we basically know these observations. So, from these observations, the task is estimate the parameters of signal. Now, there are practical examples. The signals are everywhere. So, let us say this is a speech signal, and this is a typical example of a speech signal. For wireless communication, this is a typical example of wireless signal, and then for biomedical, in this case I have taken ECG signal. This is a typical example of ECG signal. So, these signals are traditional signals people have worked on for years. Then more signals in complex scenarios in today's world or in contemporary worlds are something like signals or data over a network. For example, in this case there are several sensors, and the sensors are connected via a network, an arbitrary network. So, this signal also can be shown as a signal over a graph, and the graph is defined by the network. Then comes large financial data or transactions. For example, we buy a lot of stuff over internet, and this creates lots of data. So, that also that data is very interesting to deal with. Then social interaction data. In case of social media, in social media people interact between each other, and then also they also influence others. So, this is also a very large data and interesting data to deal with. Then comes manufacturing data. This is in the large manufacturing hubs and companies. They produce lots of data of their production line and the machines. So, that is also a data, interesting data to deal with. Then comes large biological data such as genetic data. In biological field, nowadays thanks to these cheap gene sequencing machines, they produce lots of genetic data, and they would like to get informations from this data, and this data is really huge, and this is also a very interesting data to work with. Now, I have given you several examples of data in different kinds of fields. So, how do we handle such diverse signals and large data? So, this is a natural question. So, how do we handle such diverse signals and large data? So, in big data challenges, we can ask a question that should we make customized solutions for every specific problems, or should we try to find out more general solutions by exploiting general properties? So, a natural question is again, what general properties can be exploited? So, sparsity is a key property to exploit. Signals or data may be very large, but they are sparse in nature. Say for example, this particular slide is mostly white and few portions are red and most of the portions are black and there is also blue. So, in the whole image of this slide there are few activation points shown by these blue, red and black portions. Most of the things are nothing. So, in that case this is a sparse image. On the other hand, let us say in a dark night you look to sky and we see few stars, those are the bright spots. So, those are activation points and the whole sky is dark. So, it is also a sparse image. Now, this particular slide, is a man-made signal. On the other hand, sky is natural image. So, for both man-made and natural image we have sparsity in nature. So, recent progress in analytical and algorithmic aspects allow us to exploit sparsity. So, in this slide we have mathematical representations. Let y is a vector and x is another vector, and a linear representation is y equal to phi x. What does it mean? It means we use a generative model where y the signal is produced by a linear combinations of columns of phi. In the linear combination, the linear weights are in x. Now, what happens if dimension of x is much more than y? Can we solve x? Typically no, because the system is underdetermined. What does it mean? Because the dimension of y is much smaller than the dimension of x. So, that means the number of scalars in y is lower than the number of scalars in x. Again, that means that the number of equations in these whole systems are lower than the number of unknowns. In that case, we cannot solve it in general. So, this is a pictorial representation that y equal to phi x. In this case, x is large and y is small, and we cannot solve this system. But if x is sparse in nature, then we can solve it. This is a powerful mathematical result today, meaning large sparse signal, that means large sparse signal and small observation signal, they have some kind of equivalence. And phi is a matrix which typically is a random projection, and most of the time this random projection matrix works. So, random projection and preserving information. In this slide, I explain that if x is a very large dimensional signal and this is the domain of x, from this x we go to the domain of y through this operator phi, and this is a small dimensional y. So, but still from this small dimensional y, from this domain of y, we can come back to the domain of x. That means that the information in the domain of x is preserved in the domain of y, otherwise it was not possible to come back. So, what is a possible implication? An implication can be a very large dimensional x can be projected. Of course, this has to be sparse. This has to be projected in a small dimension of y, and the processing can be done in the small dimension of y. In nature, signals are typically sparse in some domain. So, in this case, x is a signal which may be a dense signal, but that signal is sparse in some domain psi. And for example, a very large image can be sparse in DCT or wavelet domain. So, that means we can use this general form in myriad applications. Let we use canonical setup y equal to phi x. The most known algorithm called basis pursuit solves this optimization problem. That means minimization of the L1 norm of the solution subject to y equal to phi x. And often we have additive noise as an environmental noise. Now, the above is a convex optimization problem, and we can exactly solve it x in certain conditions, and this use of the L1 norm is different than standard L2 norm based methods or least square based methods. So, least square based method or L2 norm based methods are the backbone of many traditional signal processing and machine learning methods, but this use of L1 norm is different. The basis pursuit and other related methods such as lasso are in compress sensing, sparse representation, dictionary learning, and different kind of topics. And the seminal paper is by Donoho, compress sensing in IEEE transaction information theory. There exists also other kind of algorithms like computationally simple algorithms mostly use algebraic approaches, not the convex optimization approach, but algebraic approaches, and these are called greedy algorithms. And examples of greedy algorithms are matching pursuit, orthogonal matching pursuit, subspace pursuit. We have worked on that, and our algorithm is is there in IEEE transaction signal processing. This is the reference. Now we talk about machine learning and specifically Bayesian learning. Using Bayes' theorem, we estimate the posterior using likelihood and prior. So, this has general form like this. This is the posterior given your data y, and this one you want to estimate, and then this is the likelihood, this is the prior. So, we must need to use sparsity promoting prior to have a reliable solution. So, a posterior allows confidence on estimation quality. So, finding posterior is non-trivial, and associated methods are expectation maximization, sparse kernel machines, and graphical models. We recently have worked on this, and this is the reference in archive right now. So, more generalization can be done where X is a low rank matrix, it is called low rank matrix reconstruction. In the system setup, X is a very large dimensional matrix, but it has low rank. So, then X still can be a linear operator can act upon it, and then it can be projected into small dimensional y, and from that small dimensional y we can get back X. And the associated algorithms are nuclear norm based convex optimization, greedy and Bayesian machine learning algorithms. We have worked on this, and this is the reference that this is also a new current work by us, which is right now in archive. And then comes distributed estimation, and I basically talk about distributed compressed sensing. In this case, what happens is that there are several nodes, and these nodes are connected via a network. Okay, and network has links according to the available resources. Now, if the network link improves, so we go to this kind of networks, we show that the performance also improves where the nodes have the signals have correlations between each other, and this is a result that where this dimension is the subsampling factor, that means what are the number of measurements we require corresponding to the signal dimension, and this is the signal reconstruction quality. We show that this is the curve that where there is no connection, no information exchange between the network is exploited, but this is this performance slowly improves as the information exchange between the network also improves. So, this is also referred in this following paper. Then comes biological data analysis in metagenomics, it is also a big data problem. We discuss one particular application area called bacterial community composition. Suppose we have a glass of water, we want to estimate the bacteria composition in that water sample. Okay? So, this is useful in healthcare, pollution control, and many places. Now, existing machine learning algorithms are very complex. What it does, what the whole system does is that there is a gene sequencing machine which basically gives you lots of gene sequences. This is a huge amount of data, and that data the machine learning algorithms use and estimate the bacterial community into that sample. But now comes the key point. Note that any sample will have few bacteria present among all the known bacteria, right. So, any arbitrary sample if we take, in that sample there are few bacteria present. So, that means this is inherently sparse in a so-called bacteria space. We can exploit this sparsity in this framework, and then this is a algorithm we designed and published in Good Bioinformatics journal paper, as a bioinformatics journal paper, and here is the performance. In this case, all these blue colors are the real proportion of a bacteria, and then the sky blue color and the dark blue colors are the real ones, and the sky blue colors are given by the sophisticated machine learning algorithm called VBAC, and this runs over a cluster of processors over days, and you see that the performance estimation performance is quite good. And then comes this our algorithm called SEC, and this is the brown color is our performance, which is quite okay performance, slight loss of performance than VBAC, but this is much faster. Within 20 minutes on our current Dell laptop it works. Okay, while the VBAC works for a cluster of processors. On the other hand, there are other computational simple algorithms are there called Quickard and Taxi. Their performance are shown by this green and orange color, and their performance is much poorer. So, what is the conclusion? Conclusion is that sparsity is a key property in nature. It is possible to exploit sparsity in different fields, okay, and that we have shown so far. We basically talked on the signals and systems and also a bioinformatics field. Then use of sparsity is a thriving topic, it is just growing, and these hold high promise for applications with large data. That means a very large data can be projected into small dimension, and still some of the inference tasks can be executed in this small dimension. Thank you for your attention.